How's it going? Stefan here, and today we're going to derive the expression for concentration in a batch TFF concentration step. Yeah, so if you are familiar with mass balances, we can get started here. So I have here a drawing of a TFF system. And what you can see is that we have a retentate vessel here that has the properties of some mass, a concentration, and density of your solution that contains your protein or solute that you are concentrating. Then we have a pump that's drawing liquid from that vessel, pushing it across a filter, and some fraction of that solution will pass into the permeate over here. And the rest is returned through this retentate line here. Again, we have the valve. This as this closes, it adds back pressure, which is the driving force across the filter into the permeate. The permeate has concentration Cp of your solute. Some may pass through. It has a flow rate Qp, and then it has a density. Things that I should add here is the filter has an area A. Yeah. So we can get started with the mass balance. So, one thing that helps is like when you draw your diagram, you can, go ahead and draw it's been so long, I'm forgetting exactly what it's called, but you essentially can draw a boundary around your system. And this kind of helps us figure out what's going on. So we can see that there's no streams in to the system, but there is a stream out that permeate. And then we can go over to our general mass balance equation. And we'll see that there is a generation term. I just wrote gen. It's kind of a pain writing with this mouse. Yeah, so this is like your generation term or like accumulation. For our purposes here, that's going to be 0. Then we have our in term. Nothing's going into the system, so we can cross that out. We do have an out. And then there is the accumulation or just the, this is like the mass in the system over time, which we will, we do have that here. Okay, so now we can, I guess, get to writing out the actual expression. So our out term, actually, let me take a step back. The first thing we're going to do is write a mass balance for the total mass in the system as a whole. So here, what we're going to have is, I can write total mass. And this we can write as the amount of mass in the system, dm dt, over time. It changes with time. Well, that's going to be equal to the density of the solution and the change in times the change in volume over time. Okay. And that's equal to the density, the out term. Now we're writing the out term. That was the accumulation term. Now we can write the out term. So that's going to be minus, scroll up here really quick. You'll see there's a minus out. So we're going to have minus the flow rate leaving the system, QP, times the density of the solution that's leaving the system. One assumption that we are going to make for these mass balances, and it's a pretty fair assumption to make, is that the density being retained, so this one over here is equal to this one here. So these terms are going to actually, these densities are actually going to cancel. And we will be left with dV dt. So the change in volume in the system is just equal to the flow rate, the permeate flow rate, what's leaving the system. Now, the permeate flow rate, because we have this area associated with the filter, we can write that the flow rate will just be equal to the flux, which is the flow rate per area, times the filter area. Okay. So, yeah, this is the total mass balance or volume balance for the system. I'm just going to circle this because we're going to need it in just a little bit. Okay. Now we can write the mass balance for a solute in the system. So I can write the solute. I'm just going to write MBAL for mass balance. Okay. Solute mass balance. All right. So this is going to be similar to the total mass balance that we just wrote. So, okay, we have our accumulation term. So the mass of some solute, I'm just going to put an I there, some solute I over time. And that can be written as the change. So the change in the mass. So mass is equal to concentration times volume. So we can say C times V over dt. And just scrolling back up, you'll see that, the solution in the retentate side that has, mass M or like mass Mi, and then a concentration C associated with it. So that's what we're filling in there. And then this is going to be equal to now our out term, which is just going to be, the concentration in the permeate, the Cp of our solute of interest times the flow rate, QP. And now what we can do is we can rewrite this minus Cp times Qp. We can adjust that a little bit. So if you've watched my other video on sieving, you'll know that the sieving is equal to the permeate concentration over the retentate concentration, Cr. For the purposes of this video, I've just been calling CRC, so I'm going to get rid of that. We can rearrange this and write that Cp is equal to the sieving coefficient times C. And we'll, plug that in here. And then similarly to the total mass balance, we can write the flow rate out of the permeate, QP, as JA. So now I can, rewrite this again. So we'll write d CV over dt is equal to minus the sieving coefficient times the retentate concentration times JA. Okay. So now I'm going to circle this. Now we're going to take our total mass balance that we wrote above and our mass balance down here, and we're going to combine the equations to carry on here. So first I'll write, I'm going to rewrite these. So we're going to have the total mass balance and our solute. I'm just going to write them right on top of each other because I'm going to rearrange them just a little bit. Okay. So let's see how I can, okay, I'm just going to rewrite them. I was going to copy and paste, but we'll have dv. We can bring this dt over to write dv is equal to minus ja dt. That's our total mass balance. And then for our solute, we'll do the same thing. We'll bring the dt over and we'll say that d cv is equal to minus the Sivin coefficient times the concentration times J A dt. Okay. And now you'll notice that we have a, we have a minus J A dt there and, a minus J A dt in the solute. So that's how we'll combine these two equations to write the following. dCV is equal to minus SC dV. Oh, actually, I messed that up there. There's no minus sign, right? We got rid of that. We're plugging in the dV is equal to minus JA dt, and we have a minus JA dt in the solute mass balance, so we plug that in and get rid of the minus sign. Okay. Now, we can, I guess I'm forgetting what the terminology is for this, but we can essentially write out what this derivative of CV is. So, both the mass or the volume and the concentration are changing over time. So we will write V dC. This is just like a product rule, I think, times C dV is equal to the Sivin coefficient times C times dV. And now we can bring this dV over. So it'll cancel here and we'll have a dV right there. Okay. So I'll continue right here. We're going to have now V dC over dV plus C is equal to SC. Okay, so this is an important result. We're almost there. Okay, so now we're going to rearrange this. We'll bring the C over, and we'll have V dC over dV. Sorry if I write out a lot of these steps. I kind of need to, and I'm doing this on the fly. So, I want to make sure that I don't mess anything up, skip too many steps. Okay, so we're bringing this minus C or the C over to the SC side, but we can also pull it out. So I'm just going to do that all in one. So that's going to give us S minus 1. Okay. Now, we can continue to rearrange things here. What I'm going to do, a couple steps in one. I'm going to bring the C. I'm going to divide by each side by C, and I'm going to then multiply each side by the dV, and then also divide by V. So essentially, I'm going to be bringing the C over here, and then this V dV over to the right side. So let's do that. Now dc over c is then equal to sieving minus 1 dv over v. Okay, sweet. Now we can integrate both sides. This will be from the final concentration. I'm just going to call it C, or excuse me, from C naught, the initial concentration, to C, and then this will be from the initial volume, V naught, to the final one, V. So the integral of 1 over C is going to be natural log C. So we'll have natural log C, and then if you evaluate it at, the bounds, we're going to have C over C naught. And that's equal to, you get the same result for the volume. Very easy. Natural log of V, not putting in the F's, just V over V naught. Okay. And now we have some, just some algebra to do. That is, should be pretty basic, but I mean, if you haven't done this in a while, it's, you might have forgotten about some of these rules. So, okay, so we can bring this s minus 1 up here. We're going to have natural log of, that's just a property of logs. S minus 1. Okay, and now we can exponentiate both sides to get rid of that log. We're going to have C over C naught is then equal to V over V naught. And that is raised to the S minus 1. Okay, now this is a little, crafty thing to do, just to put this in, this is our solution, but you'll often see it written a different way, and we're just going to get it into that form. So I'm going to just show you what we're going to do. So we're going to have V over V naught, right? And V over V naught, that is equal to V naught over V to the minus 1, right? These two are equivalent. And I can write this here. So if you have A to the minus 1, that's equal to 1 over A. It's a terrible A. 1 over A. So that's what's going on right there. Okay, right? Everyone agrees? Well, you can do the same thing. You can say that V over V naught, and if it has this S minus 1, that's also equal to V naught over V minus 1 times S minus 1, which is also equal to V naught over V, all of this raised to the 1 minus S. Okay, and we're going to write the equation like our answer like that. The reason being is that this V naught over V is often written as X, or your concentration factor. So let's just do that, and we'll be all finished here. So we'll have C over C naught is equal to V naught over V, all of this to the 1 minus S. And again, you can write the V naught over V as X, which is the concentration factor. And that is how you get this result. You may have seen this if you're doing TFF. I know that I've shown it in my video on measuring sieving, and that is how you get this result. Yeah. So hopefully that's helpful. I just find these to like going through the mass balance. It's just a good exercise. I mean, it's really not that useful in industry, but gets you thinking a little bit and refreshes some of those old algebra skills. Um, Maybe a little bit of calculus with some basic integration. Yeah, hopefully this was helpful, and I'm gonna make a couple videos on the mass balance derivation for dye filtration as well as fed batch concentration. So yeah, those are coming up.